Hello everyone. Right, so we're going to look at work solution 3. And you notice that this is a problem where we have already told you what the reactions are at the hinge. So I've worked out those reactions, and you worked out what the reaction forces at the pivot is. So these are all external forces. The external forces are different types. These ones here have been loads, where I've put double underlined there, and these are reaction forces that respond into the loads with a single line. So that's imagining we got the body, we're applying forces to the body and the body's not moving. Now what we're interested in doing is looking inside the body and seeing if we can see what the forces are inside the body. It's very similar to how I have a piece of weight hanging from a string, and I'm looking for the tension inside that string. So what I'm going to do is we got a nice looking problem here. It looks a bit like a string problem at this particular joint. So we've got this weight coming down, and we've got, well, 4 pieces of string, we could imagine. So I'm going to assume that I've got these 4 pieces of string. I know that if my weight's coming down, that this piece of string here and this piece of string aren't going to support any of that weight. So it's going to the weight's going to be a combination of this string here or this string here. Now, of course, we're not actually referring to strings. We're referring to members, and these members can either be solid, sort of objects like this, yeah. So a solid object, or it could be, what do I need? A little bit of cable, or it could be a bit of cable like that. So it could be something that I'm trying to pull apart, or maybe something that I'm trying to squash together. So I'm going to call them members. And then what I'm going to do is I'm going to imagine that in each member there must be force travelling down it. So if this force is going off in this direction, when it hits this joint, then I will imagine that there's a force also pointing in the opposite direction. And I'm going to do that for each member I'm looking at. And what the method of joints is, so what we do is we're going to work out what the force is, whether this is in tension or in compression, and the value that we're going to get, we're going to say when we get to the other end of the joint, it's going to have a force going in the opposite direction. So any force that I say that exists inside that member will be cancelled out. So every time I work out what the force is inside a particular member, it always gets cancelled out. But that also tells me the internal force that the member is experiencing. So it's either experiencing something in compression or it's experiencing something in tension. So what we do to achieve that is we do an imaginary cut all around a particular joint. Okay, so I'm going to cut all around that joint. I'm going to include my external force here, so he gets included, this force here. But I now have these forces because I cut through the bar that I expose them and I can see what they are. So the way we do it at UE is we label up each force as if it's just letters. So we're going to say EF, we're going to put the lower letter first. So EF is a force going off in this direction here. BE is a force going off in this direction here. And CE is a force going off in this direction here. And DE is a force going off in this direction here. And what we can do is we can say, well, at that joint we can assume that the forces aren't going to move, because what we're actually going to do is called pin jointed trusts. So we're going to have a pin where we put all those members and then they go in this joint. And so looking at that particular joint there, I'm going to say that's not moving, because I can see it's not moving. So if it's not moving, that must mean that when I look at all these forces, they must all add up to 0, going off in the x direction, say, and going off in the y direction. Okay. Now, this joint here that we've got, a joint E, is not a good joint to start with. Why? Because I've got one known value, so they've got the 75, that's good, but then I've got an unknown 1, unknown 2, unknown 3, unknown 4. So I've got 4 unknowns and I've got 1 known. And I can resolve forces, adding up my forces, and I can add them up going off in the x direction. And I can add up my forces going off in the y direction. And I can't do anything else because we've just got a pin. We're only looking at the forces at a particular point, so we can't take moments or anything like that. So that means we've got 2 equations and 4 unknowns. So this is not a good joint to start with. A better joint would be either at A, because we've got 2 knowns here and we've got 2 unknowns, or we could start at D. That would be a good place to start. We've got 1 known and we've got 2 unknowns, so again that would be a good place to start. I can't see any other good places to start, so it's either going to be one of these reaction points that I want to start off doing my method of joints. And what we've chosen is to start off with the method of joint at joint A. So going back to the previous diagram, so this is joint A. It's got one force being applied to it going in the vertical direction, and we've got another force being applied to it going into this horizontal direction. So we've got a 47.5 going upwards and a 90 going left to right. And what we're going to do is we're going to imagine that we can cut through these members and we can expose their forces. And I'm always going to define that the forces, I'm going to always assume rather, that the forces are pointing away from the joint. If they're pointing away from the joint, then the force should be in tension, if it's a positive. Okay. And the reason for that is because if I'm pulling away with the external force, my internal force will be going in the opposite direction, so it would be going in the opposite direction. Okay, so I've taken a cut around the joint A and I've exposed these 2 internal forces. Notice we can start with the first letter, so AB, so that's one force, and AF, and that's my other force. So there's my 2 forces that I've now exposed. Everything else in the framework I'm not worried about. I'm only worried about the forces at that particular joint, and if there's any external forces, I need to have them there. So I need to have my reaction external forces there. So the next thing you can do with method joints, which is perfectly acceptable, is decide which is the best way to resolve. Doesn't matter, you can just plod along and you can always just resolve your forces in the x direction, because we like doing x first, and then resolve your forces in the y direction. And then we can find out what the values in A and F are. It might be a good idea to consider where these forces are going, in which direction they're going, and in which case it would be better, I think, on the whole, if you started off with this particular joint, that if you resolved the force in the y direction, because that way you've only got AB pointing off in the y direction. In the x direction, we've got AB pointing in the x direction and the AF pointing in the x direction. Now it doesn't matter which way you choose round, so if you choose it round this way, you're going to get the same result. It's just something you might want to consider when you do method of joints more and more. So what we can do to make our maths a little bit easier is we could break down the components of AB into horizontal and vertical components. So what we're doing is we can put this intermediate step. Now it depends whether you want to do this or not. You can put this intermediate step of breaking down your components in the x direction, the y direction, and then it makes, when you come to do your sum in your forces in the x direction and summing your forces in the y direction so much easier. And it only makes it easier because you're kind of pre-doing the maths before you do the maths, as it were. So it's up to you. When we do this, we've got two choices of how we're going to do this, and I'm going to choose, I think, first look at how you can do it, and it's usually this is considered the easier way of doing it, and that's using the angles and using your trig functions sine and cos. So if I'm going to resolve this force along the horizontal, I know that it's going to be that AB times by cos theta is the value going along the horizontal. So that's that force resolved. And then if I want to then resolve the force going off in this direction, well, I know that if that's theta, and I would know that well, what would I do? I'd use theta there. So we've got the opposite value that we're looking for, and we've got the hypotenuse that we're looking for. So that's going to be AB sine theta. Now, you know me, I prefer usually to use cos all the time. So if you did that, then you would have to work out what this angle is here. Can we work that angle? It's an easy one. It's a 3-4-5 triangle, so it's not an easy one to work out. So you could work out what that angle is, and then take 90, take away that angle, and find, let's call it gamma, and you could replace that with AB cos gamma if you prefer. So there's kind of two ways that you could approach this as well, this particular technique. So now I've split up my forces, one going in the x direction, one going in the y direction. Everything is nice and horizontal or vertical. Now you don't have to do this. You could skip ahead and just go straight into resolving the forces and do the maths. Okay. Now there's an alternative way that we can do. And start avoiding having to find out what theta is for our functions. And to do that, you need to look at the frame of the geometry. So the framework of the geometry tells us that we've got a theta here, we've got a length of 3 on this side, a length of 4 on this side, and it's a good practice to maybe do a little triangle like this next to your free body diagram of the joint, and then just write out what cos theta and sine theta is. So cos theta is going to be the adjacent length, so that's the 4, divided by the hypotenuse, and that's the 5. Okay, and then sine theta is going to be the opposite, divided by the hypotenuse again. That would be 5. So you've got a choice here where you can go into using hardcore maths. So we can just get rid of our sine theta and replace it with a 3/5. Get rid of our cos theta and replace it with our 4/5. The alternative is we could find out what theta is, and we could put it into our equations. So we've got choices. So here's choice number 1, is I could say, well, my cos theta, I know it needs to be 4/5, sine theta needs to be 3/5, or I could maybe use tan or cos, doesn't really matter, and use arctan and find out what the actual angle is. So there we go. So there's two options. Option 1, use hardcore mathematics. Option 2, you can play with angles. So you've seen this before in your primer. If you're going to go for option 1 using hardcore mathematics, so then we're going to replace the what do we have here? So the cos and the sine. So we're replacing the cos here and we'll replace the sine here. Okay, now I can't do anything more with this diagram. Alright, now I have to start resolving my forces, and I've chosen wisely to resolve my forces in the upwards direction because I've got two unknowns going off in the x direction. So the first force that I can see going upwards is 47.5, so it's that force there. The next force that I can see going upwards is this internal force, which is AB, and if I times it by sine theta, I now have worked out that sine theta is 3/5, and then that gives me this equation here. So just some simple algebra, and then we end up with that AB is minus, here I'm working to 4 sig fig, I suppose, so minus 79.17. So that's AB found. That's cool. So now I found AB. That means that I can now substitute that value into here when I resolve in the x direction. And here we're going to do it. So we're going to now resolve in the x direction. So we've got this external force 90. It's going left to right, so it's positive. We've decided that's our positive direction. We've got a good practice here is to not substitute in straight away, but write out the force values. So we've got AB here. It's times by cos theta. Cos theta is 4/5, so that's that term. And then AF is just pointed nicely in the in the x direction, so that's going to be AF. Now I can rearrange this, knowing that I know previously that what AB was, which that was the minus 79.17, and then I can now find what my AF is. So again, some simple algebra. Take the 90 over to the right hand side, take the 4/5 times AB over to the right hand side, substitute in the value for AB, so that's the minus 79.17, and now I can work out what AF is. Okay, so on the left, what we're doing is the hardcore maths approach, and alternatively we could play with angles. So we could play with the angles where we work out what the angle theta is and substitute in the angle theta into our calculator here. But this usually requires writing out more stuff when you do your solution, and when you're writing out your values you probably want to write them out to 5 sig fig each time. You're likely to end up with a truncation error at the end, which you can usually interpret what the value should be. So you're likely to end up with a value, let's say for example 19.999, and then you should realize, well, actually it probably means 20. So that's something reason why you should work to on the whole to 5 sig fig and present your final answer to 3 sig fig. Okay, so that will be a good rule of the thumb if you're going to do it this approach. So with this approach, we found out what the angle is. Again, we split them in one side, the other side. I don't need to know what a cos is or a sine is. I'm just going to put them into my calculator and find those numbers. So I am going to do the same thing as before. I'm going to resolve forces in the y direction. So I've got 47.5 going upwards, and I've got AB times sine 36.87 going upwards. Okay, so that's my forces resolved in the y direction. I'm going to rearrange this so that we end up with minus 47.5 divided by sine 36.87. I'm going to put that all into my calculator, and I'm going to end up with the same answer as I previously did. Now let's do the same thing going in the x direction. So this time I am going to take the force. This force here is going in the x direction, this force here, and this force here. So all those forces added up need to equal 0. So there we go. We've got the 90, the AB cos 86.7. Sorry, AB cos 36.87, yeah, plus AF. Okay, so rearrange this because I previously found what AB is. So put that on the right hand side, rearrange it, put all of that into your calculator, and then you should end up with the same result. So that's it. So, I don't know. Are you happy? Straightforward? Maybe?